In this video I'm going to be talking about QR decomposition. So QR is yet another way in which we decompose a matrix into a product of two matrices. With QR decomposition, what we're looking to do is we want to write the matrix A as a product of two matrices which are Q and R. Now Q is what we know as an orthogonal matrix. Okay. So orthogonal matrix means all of the columns of Q have a dot product equals 0. So for example, if Q was equal to something like A1, A2, where A are the actually call it Q1 and Q2 rather than A1 and A2. Okay, what we're saying is that the dot product between Q1 and Q2 is going to be equal to 0. So this essentially all of the vectors in Q are perpendicular to each other. Okay. Furthermore, each vector in Q is a unit vector, so their dot product is going to be equal to 1. So Q1 dot Q2 is equal to 1, and Q2 dot Q2 is also equal to 1. So that's what we mean by orthogonal. Now R is simply an upper triangular matrix, so similar to U in LU factorization. Triangular. Okay, so that's what we're seeking to do. Many advantages for doing this, and later on I'll show you an example of what one of those advantages are. Okay, so we mentioned that the vectors or the columns of Q are all perpendicular to each other. So one way in which we can do this is use what's called the Schmidt process. So Schmidt. Okay. So what we have is, let's say we have two vectors. Let's say we've got a vector A1 and we've got a vector A2. Okay. Now what I want is I want a vector or a set of vectors which is in the same span as A1 and A2, but are perpendicular to each other. Okay, so I'm going to say we're going to say let U1 and U2. So I'm going to say U1 and U2 are going to be need to be perpendicular to each other. Okay, so first thing we do is we can let A1 equal U1. Okay, so that's our first vector. That's easy enough. So now what I want is I want a vector which is going to be perpendicular to A1 in the same span. Okay, and I'm going to call this U2. So how do I get U2 from A1 and A2? Well, we use vector projection. Okay, so if I project the vector A2 onto A1, okay, so this is the projection of A2 onto U1. Okay, so it's kind of like, I like to think of it as like a cast in a shadow. So that's that projection there. If I negate this, so that if I turn this vector around and add it to A2, okay, we get that. So that's going to be minus the projection of A2 onto U1. Okay, so what we can say is that U2 is equal to the vector A2 minus the projection of A2 onto U1. And that's called the Schmidt process. So every subsequent vector, so let's say if we had vectors R3, let's say we had another vector and we had another A vector, what we would do is we'd want that vector U3 to be perpendicular to both U1 and U2. So what we'd have to do is we'd have to subtract the projection of A3 onto U1 and also the projection of A3 onto U2. And we keep going for however many columns are in our matrix A, we keep doing this. Okay. What I'd advise you do is just check out the lecture notes for the full sort of derivation. But what I'm going to do is just summarize this. So this is QR, and this is using what we call the Schmidt process, so often known as QR Schmidt. Okay, for column 1, so for the first column we simply have R11, which remember R is our upper triangular matrix, is, so R11 is whatever the magnitude of our first column is, and we have Q, our vector Q1, which is our first column of Q, is going to be our vector A1 divided by R11. Okay, so in other words, Q1 is the unit vector pointing in the same direction as A, because remember we wanted all of our columns in Q to be unit vectors, and R11 is the magnitude of vector A. For all other columns, so for columns J equals 2 to how many columns we've got, let's say we've got n columns, okay, we calculate Rij, and that's going to be our vector Qi dot product with the vector Aj. So Q is what we calculated on the previous column, so Qi is usually what we calculated on the previous column. Aj is the jth column of A, and so we do that from 1 to j minus 1, to all the previous columns. Then we have our uj vector, and that's going to be equal to aj minus the summation of all the previous columns, i equals 1 to j minus 1, of rijqi. Okay, so this is that Gram-Schmidt process. This is subtracting all of that from our current vector A. Once we've done that, our Rjj, which is, remember, the upper triangular, it's an element on the main diagonal of the upper triangular matrix, is the magnitude of uj, and finally qj is equal to that uj we just calculated divided by rjj. Okay, so it is quite an involved process. So for the first column it's fairly easy. For all other columns we have to follow this. Okay, so like with everything, it comes a bit easier, or it's a bit easier once we have a look at an example. So I'm going to follow the example 6.14 in the notes. Okay, so at 6.14 I've got a 4x3 matrix, minus 1, minus 1, 1, minus 1, 3, minus 1, 3, and 1, 3, 5, 7. Okay, first thing you notice here is this is a 4x3 matrix. Now, all of the other decomposition methods we've been looking at always require a square matrix. So one of the main benefits of QR decomposition, it allows us to rewrite an n by n matrix into Q multiplied by R, which is useful for solving some systems. Okay, so first I'm going to look at column J. J equals 1, sorry. That was quite easy. So we saw that the first value of R is the magnitude of A1. So in this case that's going to be minus 1 squared plus 1 squared plus 1 squared plus 1 squared. So we got R11 is equal to 2, and Q1 is equal to A1 divided by R11. Okay, so that's going to be obviously that's going to be minus a half, 1 half, minus a half, and 1 half. Okay, so that's our first column of Q, and that's our first element, row 1, column 1 of R. Now, if we move to J equals 2, okay, so R12 is Q1 dot product with A2. So we just calculated Q1, so that's minus a half, minus a half, and have I got too many minuses there? Yep. So I just quickly sort of try and get rid of that. Yeah. So there was an erroneous minus coming there, so that should be a half. And that's dot product with A2, so that's the second column of A. So it's minus 1, 3, minus 1, 3. Okay, if you calculate that, so we got minus a half, plus 1.5, so that's 1, plus a half, that's 1.5, plus 3 over 2, so that's 4. Okay, so that's the element row 1 column 2. So now we've got to calculate U2. Okay, I don't go any further here, so just R12 is what we need, because now we need to calculate U2. So U2 is equal to A2, now this is that Schmidt step, minus R12 multiplied by Q1. So A2 is minus 1, 3, minus 1, 3, minus R12 is 4, and that's multiplied by Q1, which is minus a half, minus a half, and a half. Okay, so minus 1 plus 2 is 1, 3 minus 2 is 1, minus 1 plus 2 is 1, and 3 plus 2 is oh yeah, I've got that. For some reason I keep putting that minus in, don't I? Keep getting a bit carried away with my minuses, so I just correct that. That was plus a half. So 3 minus 2 is 1. Okay, so that's our U2. Now R22 is the magnitude of U2. So that's just root 4, which is obviously 2. And therefore that gives us Q2, which is U2 over R22. So that's going to be 1/2 times whatever U2 was. That was all the ones. So that's going to be a half, a half, a half, and a half. Okay, so that's the first 2 columns done. Okay, so I'm going to move on to the third one. So this is for J equals 3. Okay, so we've got R13, and we also need to calculate R23. So R13 is going to be Q1.A3. Okay, so if you recall, Q1 was minus a half, minus a half, and 1/2. Hey, no, I didn't put the minus then. Good. That's dot product with the third column of A, which was 1, 3, 5, 7. Okay, so we've got minus a half, plus 1.5, that's plus 1, minus 5 over 2, which is minus 1.5, plus 3.5, that's 2. Okay, so R23 is Q2.A3. Okay, so Q2, we just calculated that was all the halves. And dot A3 is the same, so it's 1, 3, 5, 7. Okay, so because these are all the same, if I sum this, we get 12, 16, half that is 8. Okay, so now we've got the Schmidt step, so we're calculating U3, so that's got to be perpendicular to all the, so it's got to be perpendicular to both Q1 and Q2, so it's going to be R13 times Q1 minus R23 times Q2. So A3 is 1, 3, 5, 7. R13 is 2, and that's multiplied by Q1, which was minus a half, minus half, and a half. That's minus R23, which is 8, and that's multiplied by all the halves. Okay, so if we do that, we get minus 2, 2, and 2. So we need to, so R33 is simply the magnitude of that. So that's going to be 4 plus 4 plus 4 plus 4, so that's going to be root 16, which is of course 4. So therefore Q3 is going to be U3, so there's no magnitude, it's just U3 over R33. So it's going to be 1/4 whatever U3 was, which is minus 2, 2, 2, and 2, which is minus a half, half and half. Okay, so we have Q1, Q2 and Q3, and we all have all of our R's. So Q1 was minus a half, minus a half and a half. So that was Q1. Q2 was all positive halves. So that was Q2. And finally Q3 we just calculated was minus a half, minus a half, a half and a half. So that's Q3. And our R, well, R11, if we recall what R11 was, that was 2. So R11 was 2. And because it's upper triangular, we have nothing beneath it. R12, just trying to recall that what R12 was 4. And R22 was 2. That's 4. 2, 0. R13 was 2. R23 was 8. And R33 was 4. Okay, so we have Q and R. So just double check that gives us what we're expecting. So we've got a half times 2. So that's minus 1. So half times 2. Minus half times 4 is minus 2. And 1 is minus 1. Okay. And a half times 2 plus a half times 8 minus a half times 4, that gives us 1. Okay, so all I'm doing here is just multiplying everything just to double check we got it correct. So a half times 2 is 2 plus half times 2, so that's going to be 3. Half times 2 is 1, a half times 8 is 4, so that's going to be 5 minus 2, so that's going to be 3. That's going to be minus 1, and that's going to be minus 1. Minus 1 plus 4, sorry, minus 1 plus 4 is 3, plus 2 is 5. And finally, half times 2 is 1. Half times 2 plus, that's going to be 3. And half times 2 is 1 plus 4 plus 2, that's going to be 7. And that gives us our original matrix A. Okay, so that's QR factorization using the Gram-Schmidt process. So all of these, all of the columns in Q, first they're all unit vectors. So if I was to calculate the magnitude of each column in Q, you get 1. And also they're perpendicular to each other. So Q.2 or Q.3 or Q1.Q3 or Q1.Q2 or Q2.Q3 should all be 0. Okay, and R is just your upper triangular matrix.